How does the CPU calculate 1 plus 1? This is actually a very complex issue. The CPU can perform calculations mainly based on billions of transistors inside. So how do transistors perform calculations? This is a p-type semiconductor. By doping, we can have two types of semiconductors. Next, we add a conductive layer between two n-type semiconductors. And by isolating it, we get the control gate. Then, on the two n-type semiconductors, we have two electrodes, which are the source and drain, respectively. So, we have a complete transistor. When we connect the source to the source, the current cannot reach the drain. But once we connect the control gate to a source, the channel between the two n-type semiconductors will open, allowing the current to reach the drain. Now we connect the source of the two transistors to a source. Whether the control gate is sourced or not is controlled by two switches. Then, we connect the drains of the two transistors, each connected to a light bulb. So, we have a simple circuit. Currently, even if we open the switch of the first transistor, the second switch, or both switches, the light bulb will light up. But when we turn off both switches, the light bulb will not light up. Now we will improve the circuit by connecting the drain of the first transistor to the source of the second transistor. This will create an AND gate. When we only open the switch of the first transistor, the light bulb will not light up. If we only open the switch of the second transistor, the light bulb will not light up either. Only when both switches are open, the light bulb will light up. Besides forming OR and AND gates, we can also implement NOT and XOR gates. NOT gates are easier to understand, where the input and output are opposite. XOR gates are relatively complex, formed from OR gates, and NOT gates, combined to build. When both inputs are powered, the output has no current. Only when one input is powered, the output will have current. For convenience, we have simplified the XOR gate into this symbol. Now we start using the previously mentioned gate circuit, combined to create a set of gates capable of performing calculations. Here are two light bulbs and two control switches. We just need to place them here, add an AND gate circuit, then connect to the left light bulb. Now we can control the light bulb through the switch. Next, we place them here, continue adding an XOR gate circuit. By now, a logic gate circuit capable of addition has been completed. The combination of this logic gate circuit is called a half-adder. Of course, there are more complex full-adder circuits. We'll talk about this later. So how does this half-adder calculate 1 plus 1? This is a piece of program code. The program code, after being compiled, will be decoded into an obscure assembly language. The assembly language is then translated, resulting in machine language, namely binary. Similarly, when we calculate a plus b, the computer will execute this line of code as adding a and b, translated into assembly language. The meaning of these three lines of assembly language is to load the value from position 10 in memory, then add the data at position 11. The calculation result is stored in position 12 in memory. Then, the assembly language is translated into binary. Finally, the binary is stored in memory. Since memory is 8-bit binary, it is a storage unit. So, every two lines store one instruction. Now let's take an example with the operation 1 plus 1, see how the CPU computes it. This is the internal structure of the CPU. At the top is the program counter, mainly used to store the address of the memory containing the instruction. When the calculation starts, the memory address register. First, it will get from the program counter. Get the memory address value of the instruction as 100. Then, the memory address register will be based on the address value of 100. Read the instruction from memory. Then, set the instruction to the memory buffer register. For easier understanding, here, we still replace binary with assembly instructions. Then the instruction will be moved to the instruction register. Meanwhile, the program counter will change to 102, meaning the address value of the next execution. Then, the command will be sent to the control unit for interpretation. After interpretation, the control unit will understand. This command needs to load data from position 10 in memory. Then, the control unit, through the memory address register, get the binary value 1 from position 10. Read into the memory address register. Next, send the value 1 to the accumulator. The load 10 command has been executed. Continue executing the add11 command. The execution is similar to the load 10 command, both are reading data. But when the command comes to the control unit, the accumulator will send the value 1 to the processor. Then, interpret and execute the ADD11 command. So, the binary value 1 from position 11 is read into the memory address register. Then, from the buffer register, send the value 1 to the accumulator. Finally, send it to the processor. Now comes the important moment. Before, it was all about reading data. What is actually used for computation is this processor. The processor consists of a half adder. Now we will send 1 and 1 to the half adder. 1 represents turning on the switch. So both switches will be turned on. Let's analyze the specific output result. First is the OR gate here. As mentioned earlier, the OR gate only needs one switch to be turned on. The new circuit conducts electricity. So when the input is 1 and 1, the output result of the XOR gate is 0. The light will not light up. For the AND gate circuit below, because the input is 1 and 1, so the output of the AND gate is 1. So the light will light up. Light on is 1. So the resulting binary is 10. The corresponding result for 10 is decimal number 2. Then return the calculation result to the accumulator. Next, start executing the store 12 command. The previous execution is still the same. When executing to the control unit will interpret this store 12 command. The meaning of the command is to store the calculation result in memory address 12. Then the accumulator, send the calculation result 2 to the memory buffer register. Finally, store the result 2 in memory position 12. From there, calculate the value of 1 plus 1. It should be noted that in reality, the CPU processor is very complex. This video only explains at the most basic level. Do you find the CPU computing 1 plus 1 understandable?